Hey guys, good evening and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So people, quickly let me know in the chats if all of you can hear me. If I'm perfectly audible, visible to every one of you. Quickly let me know in the chats. Good evening everyone. Good evening and welcome back. So quickly let me know in the chats, people, with some fire emojis. Yeah, I want fire in the chats. If all of you can hear me, if I'm perfectly audible, visible to every one of you. Good evening guys, good evening. Good evening and welcome back. Good evening and welcome back. Perfect. So my dear students, as you all must be knowing, today we are going to do one of the most important chapters of your chemistry. That is your general organic chemistry, right? Okay. Well, I think I'll be taking almost like 3 to 4 hours. 3 to 4 hours I'll take to complete this particular chapter. But the point is, I would want you guys to be with me till the end. Are you ready for that? Are you ready for that? Then only I'm going to start the session. Are you ready for that? Someone is saying, sir, feeling stressed. There is no need to feel any sort of stress. Do not think about the consequences. Do not think about the results. Just make sure you are utilizing these 75 to 80 days in a proper way, right? Do not think about anything else. Do not think about the consequences. Do not think about whether you are going to get selected or not. No, just follow the process. Just follow the process. Do not keep any stone unturned in the upcoming 70 to 75 days. Okay? Sir, will isomerism be covered in this chapter? See, this is GOC. Isomerism will be separate session. There will be one shot for isomerism as well, which is going to be our next one. Okay? Which is going to be our next one. So are you all ready with your pen and paper? Let me know in the chats quick. Are you all ready with your pen and paper, people? Are you all ready? Are you all ready? Quick. Perfect. Okay, before starting, tell me how many of you are done with the last chapter which I took, atomic structure? Just tell me that in the chats. Sir, atomic structure notes not provided. Did I not share the atomic structure notes with you? Did I not share the atomic structure notes on Telegram? If not, I'll do it right after this session, okay? I'll do it right after this session, don't worry. Right after this session, I'll do. Okay, got it. Perfect then. So let's get going. Let's get started with the chapter. That is your general organic chemistry. Again, one of the high weighted chapters, I must say, right? Like 3 to 4 questions are asked from this particular chapter. 3 to 4 questions will be asked from this particular chapter. So watch this particular session till the end so that you can cover those 4 to 5 questions easily, right? And the questions which are asked from your general organic chemistry, majority of the times, they are like very easy questions, okay? They're very easy questions. And let me tell you, in this particular session, everything is going to be like, I'll be giving you the information in a very precise way. Whatever things are required in GOC, I'll be just teaching those things. Whatever questions, whatever topics are asked in GOC, I'll be covering those topics. Perfect. No irrelevant stuff, nothing, straight to your NEET examination. Okay? Perfect, guys. So, I'll be starting with the first topic of the session. What is that going to be? My dear students, that is going to be inductive effect. I'm pretty much sure all of you must have heard this particular term before also. Inductive effect. Let's exactly get to know what this inductive effect is all about. What are its applications? And what kind of questions can be framed from inductive effect. All right? Have a look, my dear students, what I'll be doing over here. For example, imagine that I have got a carbon chain over here. Imagine that this is my carbon chain, which consists of 1, 2, 3, 4, 5 carbon atoms. Okay. Let's say this particular carbon is attached with hydrogen atom. Let's say this particular atom is attached with hydrogen atom. I've got a carbon chain which consists of only sigma bonds, right? And this terminal carbon atom is attached with hydrogen atom, correct? Now, my dear students, what exactly I'm going to do? Let me just do one simple thing. Let me write the carbon chain again. This is your carbon chain, okay? Now, let me replace this hydrogen with some atom X. I've just replaced the hydrogen atom by some atom X. Okay, this is one of the scenario. Second scenario, in the same carbon chain, I'm replacing this hydrogen with the atom Y. Okay. So over here, I've taken a carbon chain wherein this particular carbon is attached with hydrogen. Yes, perfect. Now I've replaced this hydrogen by some atom X, and here I have replaced the hydrogen by some atom Y. Okay, point number 1. Sir, aap HMT se ho? Ji. Yes, I'm from the same place. Okay. Now, my dear students, just try to understand one thing. Imagine that electronegativity of X. Imagine that electronegativity of X is greater than that of electronegativity of carbon. Imagine if X is more electronegative than carbon. What is going to happen? If X is more electronegative than carbon, I would say this X will attract the bonded pair of electron towards itself, due to which this X gets delta negative and this carbon gets delta positive. Correct? Now, this carbon carrying delta positive, it's going to attract this electron pair towards itself, due to which this carbon also gets delta positive. Now, this carbon carrying positive attracts the electron density towards itself, due to which this particular carbon also gets delta positive. Right? Okay. Now, my dear students, for example, this Y which I have attached over here, let's say electronegativity of carbon is greater than that of electronegativity of Y. This is one more scenario. If electronegativity of carbon is greater than that of Y, so what this carbon is going to do, it will attract the electron pair towards itself, due to which this carbon gets delta negative and this Y gets delta positive. Perfect. Now, my dear students, I would say this carbon carrying delta negative, it's going to repel this electron pair, due to which this carbon also carries delta negative. Similarly, this carbon also carries delta negative. So if you look carefully, when I replace this hydrogen with some atom X or some atom Y, what happened? I say the chain got partially polarized. The chain got partially polarized here as well as here. Right? I would say the carbon chain got partially polarized due to what? Due to the transmission of sigma electrons. I would say when I replace this hydrogen with some atom X or some atom Y, I would say chain got partially polarized due to the transmission, due to the displacement of the sigma electrons. My dear students, whenever an atom or group is attached to the carbon chain, whenever an atom or some group is attached to the carbon chain, due to which the chain gets partially polarized, due to the transmission of sigma electrons. This effect is something which you call as inductive effect. This effect is what you call as inductive effect. Am I clear? Did you just get the idea of what this inductive effect is all about? If I write a statement about it, I'll say whenever an atom or a group is attached to the carbon chain, the chain gets partially polarized. the chain gets partially polarized due to the transmission of sigma electrons. Due to the transmission of sigma electrons. And this phenomenon, this effect, is what you call as inductive effect. I hope this particular point is clear to everyone. Point number one. My dear students, point number two. Point number two. What do you think about this X? Is it withdrawing the electron density from the chain? Yes, this X is withdrawing the sigma electron density from the chain. This Y is pushing the sigma electron density in the chain. This X is withdrawing the sigma electron density in the chain. This Y is pushing the sigma electron density in the chain. I would say that particular atom or group which decreases the sigma electron density in the chain, we say that atom or group shows minus inductive effect. Minus means electron withdrawing. Okay. This particular group, it pushes the sigma electron density in the chain. I would say that particular group, that particular atom or group that pushes the sigma electron density in the chain, that increases the sigma electron density in the chain, we say that group shows plus inductive effect. If this was electron withdrawing in nature, this particular Y is going to be electron donating group over here. I would say this is electron donating in nature. So my dear students, when we talk about the inductive effect, we have got two things over here. One is going to be plus I, one is going to be minus I. When do I say that the group is showing plus I, and when do I say that the group is showing minus I? When the group increases the sigma electron density in the chain, we say the group is showing plus I. When the group decreases the sigma electron density in the chain, we say that group is showing minus I. Plus means donating, minus means withdrawing. Am I clear with this? Am I clear with this, people? Quickly in the chats. Everyone. Everyone, people. Yeah? Perfect. This was our point number one. So I believe that these two statements are absolutely clear to you. That group or atom which decreases the sigma electron density in the chain shows minus I effect. That group or atom which increases the sigma electron density in the chain shows plus I effect, right? Now there are a few things which you need to remember right now. What are those things? My dear students, all the cationic groups, those groups which carry the positive charge, all your cationic groups, they are going to show which effect? They are going to show minus I effect. So what are basically the minus I showing groups? First category, all the cationic groups will show minus I effect. All the cationic groups will be minus I showing in nature. Point number one. Point number two, minus I power of the cationic group. Minus I power of the cationic group is always greater than that of minus I power of the neutral group. Minus I power of the cationic group is always greater than that of minus I power of your neutral group. This is point number two. Point number three, all your halogens, group 17, fluorine, chlorine, bromine, iodine, all your halogens, which effect do they show? They show minus effect. They show minus inductive effect, right? They are electron withdrawing in nature. So first of all, these 3 points are very important. Number one, all your cationic groups, they are going to show minus inductive effect. Minus I power of the cationic group will be greater than that of minus I power of the neutral group. All your halogens, they are going to show which effect? They are going to show minus inductive effect, right? Now, my dear students, groups like OH, NH2, NO2, CN, all these groups, what they are going to show? They are going to show minus I effect. They are going to show minus I effect. For example, if I take the case of NO2, let's say I'm taking the case of NO2. Let's say this is your carbon chain. Let's say with this carbon chain, you're attaching NO2. With this carbon chain, you're attaching what? NO2. Now, nitrogen is more electronegative than carbon. If nitrogen is more electronegative than carbon, I would say the electron density will shift towards nitrogen. This would be delta negative. This would be delta positive. This would be delta positive. Similarly, this is going to be delta positive, right? Because nitrogen is more electronegative than carbon. Instead of NO2, for example, let's say you're attaching OH. Oxygen is more electronegative than carbon. So again, the same things will happen, right? Again, the same things will happen. For example, you have got CN. Let's say you have got CN here. This is C, triple bond N, right? This carbon, it's sp hybridized. This carbon, it's sp3 hybridized. Perfect. And you must be knowing electronegativity of sp carbon is greater than that of electronegativity of sp3, right? Due to which, again, the same things will happen. Shifting of sigma electron density will take place. So all these groups over here, what do they show? They show minus inductive effect. They decrease the sigma electron density in the chain. They decrease the sigma electron density in the chain. So these groups over here which are mentioned, what are these? They are the ones which are going to show minus inductive effect. Am I clear with this? Say yes or no in the chats quick. Say yes or no in the chats quick. Now, my dear students, all your anionic groups, those groups which carry negative charge, all your anionic groups, which effect they are going to show? They are going to show plus inductive effect. They are going to show plus I effect. Remember this particular point. All the anionic groups, those groups which carry negative charge, when attached to the carbon chain, they increase the sigma electron density in the chain. That's why we say all the anionic groups, they show plus inductive effect. They show plus inductive effect. Now, my dear students, like I said, in case of cationic groups, similarly, let me tell you plus inductive effect of anionic group. Plus inductive effect of anionic groups is always greater than that of plus inductive effect of the neutral groups. Okay. All your alkyl groups, which effect do they show? They show plus inductive effect. For example, this CH3, this is your methyl group. It is attached with the carbon chain. Whenever you see an alkyl group attached with the carbon chain, right? This alkyl group is always going to show plus inductive effect. This is always going to be electron donating in nature. Well, these are some basic things, my dear students, which you must remember, right? Well, apart from these basic things, there are a few more things which you must know. As I told you, your alkyl groups, they show plus I effect. Alkyl groups show plus I effect. Now remember, plus I power is directly proportional to the number of branching at the free valent carbon. What does that mean? Let's say, my dear students, this is one group. And it is attached with the carbon chain. Here, for example, you have got a carbon chain, right? And this particular group is attached with the carbon chain. First of all, this particular atom, which is directly attached with the carbon chain, I'll be calling this as the free valent atom. Perfect. Now, plus I power of the group is directly proportional to what? Number of branching at the free valent carbon. My dear students, how many branches do you see at the free valent carbon? This is one. This is second one. So there are two branches attached here with this free valent carbon. Now, in this particular case, if you look at this particular one, this is your free valent carbon, and how many branches are attached here? There are 3 branches attached. More the branches attached, this is the carbon chain here. More the branches attached, more is going to be the plus I power of the group. So these were the two groups over here. Now, if I ask you which group has got more plus I, you will say this particular group over here, it has got more plus I power, right? Perfect. So all your alkyl groups, they show plus inductive effect, number one, right? And plus I power is directly proportional to what? It is directly proportional to number of branching at the free valent carbon. Perfect. I believe this is clear. Now the point is, if the branching is same, at that point of time, what do we do? How do we check which group has more plus I, which group has less plus I? My dear students, over here, I have selected some 3 groups. 1, group number 2, group number 3. Perfect. Let's say this particular group is attached with the carbon chain. Let's say this particular group is attached with what? It's attached with the carbon chain. Similarly, this particular group is also attached with the carbon chain. Similarly, this particular group is also attached with the carbon chain. If the branching is same, then plus I power is directly proportional to number of carbon atoms. First of all, this is my free valent carbon. It has got only one branch attached. This is my free valent carbon. It has got only one branch attached. This is my free valent carbon. It has got only one branch attached. Now, where do you see more carbon atoms in the branch? In the last case, so this particular group will be having more plus I power. So if the branching is same, that particular group which contains more carbon atoms will be having more plus I power. Am I clear with this? Am I clear with this, people? Am I clear with this? Am I clear with this particular point? And my dear students, you know, hydrogen, how many isotopes it has? Hydrogen has 3 isotopes. Which all? Protium, deuterium, tritium. Protium, deuterium, tritium. Well, plus I power of tritium will be more than that of plus I power of deuterium, which will be more than that of plus I power of protium. Okay, remember this particular point as well, because you'll be getting questions from this statement as well. Okay, these are some very important statements which I'm telling you. Now, my dear students, before showing you the questions, you need to remember the plus I series as well as the minus I series. Before doing the questions, you are supposed to remember the plus I series as well as the minus I series. When you talk about the minus I series, NF3 positive will be having maximum minus I power, followed by NR3 positive, followed by NH3 positive, followed by NO2, followed by CN. So this particular series is supposed to be remembered. Without this series, you cannot solve the questions. Okay, this series is to be remembered. This is the minus I series of these different groups over here. NF3 positive has got maximum minus I power, followed by NR3 positive, NH3 positive, NO2, CN, similarly CHO, COOH, FCl, BRI, right? This is the series which you have to remember. Number one. Number two, this is one more series which you have to remember, that is for your plus I. This is your plus I series. This is your plus I series which again is to be remembered. CH2 negative, maximum plus I, followed by NH negative, O negative, COO negative, 3 degree alkyl, 2 degree alkyl, 1 degree alkyl, right? So my dear students, this series again has to be remembered. This series again has to be remembered. So two series, one is your minus I series, one is your plus I series. Now you must be thinking, why NF3 positive has got maximum minus I, right? After this, why NR3 positive comes? We are not supposed to go into those details right now. Okay, you just have to remember the series and accordingly we can solve the questions. That's all. That's all. Why this comes first, why this comes second, all that time is over, right? We are not supposed to go there, nor that is asked in your examination. Now, my dear students, what is the important thing? Important thing is the application part. Important thing is the application part of the inductive effect. First of all, let me tell you. When you talk about the stability of the carbocation, you must have heard sometimes carbocation is stabilized by electron donating groups. Carbocation is stabilized by electron donating groups. Electron donating means plus I or minus I. Definitely plus I. So I would say stability of the carbocation is directly proportional to plus I and automatically it's going to be inversely proportional to minus I. This is point number one from which questions can be framed. Point number one. Point number two. What is that? That is stability of Carbanion. Stability of Carbanion. Your Carbanions, they are stabilized by electron withdrawing groups. Your Carbanions are stabilized by what? They are stabilized by electron withdrawing groups. Now, withdrawing means minus I. So, directly proportional to minus I, inversely proportional to plus I. This is our second question, which will be framed. Okay, this is our second question which will be framed. Similarly, my dear students, the third question, acidic strength. Acidic strength. Acidic strength. Remember, it's directly proportional to electron withdrawing groups. That means it's directly proportional to minus I and inversely proportional to plus I. Directly proportional to minus I and inversely proportional to plus I. Similarly, if I talk about your basic strength, if I talk about the basic strength is increased by electron donating groups. Electron donating means it will be directly proportional to plus I, inversely proportional to minus I. These are the things which are to be remembered. And if you remember these things, you will be easily solving the questions. First of all, look at this particular table. Look at this particular table, my dear students. Number one, stability of carbocation. Carbocation is stabilized by electron donating groups. Electron donating means plus I, so directly proportional to plus I. Carbanions are stabilized by electron withdrawing groups. Electron withdrawing means minus I, so directly proportional to minus I. Acidic strength, directly proportional to withdrawing groups, so directly proportional to minus I. Basic strength, directly proportional to donating groups, so directly proportional to plus I. Okay. Now, by having a look on these four things, I believe you can easily solve the questions. So, let's directly jump into question number one. Let's directly jump into question number one. Can you tell me what is going to be the answer of the first question? Everyone in the chats, I want you guys to be active in the chats quickly. I want you guys to be active in the chats. Tell me guys, quickly. This is something which you can easily solve. First of all, look at all these questions. Some basic questions these are, and these are the types of the questions which are asked to you in the examination. First of all, if you see, this is your carbocation, carbon carrying positive, carbon carrying positive, carbon carrying positive. Okay. Over here you have got CH3 group attached. Here you have got CD3 group attached. Here you have got NO2 attached. Okay. Now, my dear students, tell me one thing. NO2. Is it electron donating or withdrawing? It's withdrawing. It shows minus I over here. It's going to show minus I. CD3. D means deuterium. Okay. It shows plus I. Even this shows plus I. Even this shows plus I. Now tell me one thing in the series. First of all, I told you carbocations are stabilized by electron donating. This is electron donating. This is electron donating. Which one is more electron donating? Which one is more electron donating? I would say CD3 is more electron donating, right? So stability of B is going to be maximum followed by A followed by C. This is the order. Look at the second one. Look at the second one, my dear students. This is again which can be easily solved. Carbon carrying positive, carbon carrying positive, carbon carrying positive. Over here you have got NO2 group attached, right? Withdrawing. Again here you have got NO2 group attached, withdrawing. But here withdrawing group is closer. Here withdrawing group is closer. So its effect will be more. Its effect will be more. And you know, electron withdrawing groups, they decrease the stability of carbocation. They decrease the stability of carbocation. So C is going to be least stable, followed by B, followed by A. This is going to be the order. Done? Right, people? Someone is saying ortho effect. Do not introduce all these effects. Fancy terms, do not introduce here. Tell me the answer of this third question. Tell me the answer of the third question, quick. Guys, you have to be very active in the chats. Tell me the answer of the third question. You have to arrange these carbocations again as per the stability order. CD3, electron donating. CD3, donating. Where is electron donating group more closer? In the last case. And you know, electron donating groups, they increase the stability of carbocation. So C is going to be maximum stable, followed by B, followed by A. Yes? Done? Look at the next one. Look at the next one. Carbon carrying positive, carbon carrying positive, carbon carrying positive. Here do you see alkyl group is attached. Here also alkyl group is attached. Here also alkyl group is attached. And alkyl groups, I told you already, they show plus inductive effect. They show plus I effect, right? Now tell me, which alkyl group among these three will show more plus I? Look at the free valent carbon. This is your free valent carbon. It has got more branching. More branching means more plus I. More plus I means more stability. So B is maximum stable, followed by C, followed by A. Am I clear with this? Everyone. Everyone in the charts. Yes? Perfect, guys. Tell me the answer of these two questions very, very, very quick. Tell me the answer of these two questions very quick. First one. Again, you have got carbocations. You have to arrange them as per their stability, right? First of all, do you see this is your alkyl group? Shows plus inductive. Nitro shows minus I here. CN again shows minus I here, right? And you know, plus I increase the stability of carbocation. So A is maximum stable. Now, among B and C, which one? I would say C would be more stable, B at the end, because nitro shows more minus I. Okay. Now, among these two, which one? Quickly, people. You should be able to answer this question as well. This is your carbon carrying positive. This is your carbon carrying positive, right? Do you see here's a double bond attached? So more S character. More S character means more electronegativity. More electronegativity means more withdrawing. And due to the electron withdrawing nature, stability of carbocation decreases. So I would say B is going to be more stable than that of A. Yes? B is going to be more stable than that of A. Perfect, people. Let's have a look on one more set of questions. Look at this question and look at this question. Give me the answer of these two. Quick. Very quick, people. First of all, again, we have got carbocations. We have got CD3 here. We have got CH3 here. We have got CT3 here, right? Okay. Now, you know it already. CT3 shows more plus I, followed by CD3, followed by CH3. So tell me the answer, everybody. So C is going to be maximum stable, followed by A, followed by B. Yeah? I hope I'm clear to everyone. Look at the next question. Next question, people. This is carbon carrying positive, carbon carrying positive, carbon carrying positive. Here nitro group is attached. Here fluorine is attached. Okay. And here you have got alkyl groups attached. Perfect. And you know, electron withdrawing groups, they decrease the stability of carbocation. Electron withdrawing groups, they decrease the stability of carbocation. So which carbocation is going to be least stable? B is going to be least stable, right? B is going to be least stable. Here comes C, here comes A. This is going to be the stability order. Basic questions which you are directly solving with the help of inductive effect. Nothing else. Tell me the answer of these two questions quick. These are not your carbocations. These are not your carbocations. This is carbon carrying negative charge. Carbon carrying negative. Carbon carrying negative. So these are your carbanions. These are your carbanions. Everybody. And you know, carbanions are stabilized by electron withdrawing groups. Carbanions are stabilized by electron withdrawing groups. See, this is electron donating. This is withdrawing. This is withdrawing. This one is more withdrawing. If this one is more withdrawing, I would say it will increase the stability of carbanion to the maximum. So C is going to be maximum stable, followed by B, followed by A. Everybody? Yes? Perfect. What about this particular question? What about this particular question? Again, you have got three carbanions. NF3 positive, NF3 positive, minus I, withdrawing, F, withdrawing, right? CD3, donating. And you know, electron withdrawing groups, they increase the stability of carbanion. Now, which one is more withdrawing? NF3 positive is more withdrawing. So stability of A is maximum, followed by B, followed by C. Is it clear to everyone, people? Is it clear to everybody? Say it in the chats quick. Say it in the chats quick. Say it in the chats quick. Tell me the answer of these two questions again. Tell me the answer of these two questions again. Tell me the answer of these two questions again. See, you have to arrange them as per the acidic strength. As per the acidic strength. Acidic strength. And I have told you already, when it comes to the acidic strength, electron withdrawing groups increase the acidic strength. So directly proportional to minus psi, inversely proportional to plus psi. This is something which has to be in your mind. That's it. Here, some electron withdrawing group is attached. Here, hydrogen is attached. And CH3 is attached. Okay? Now check it out. Check it out, people. You tell me the answer. You tell me the answer. Acidic strength is directly proportional to electron withdrawing, right? So, where do you see withdrawing? A. Perfect. So, A is going to be maximum acidic, followed by B, followed by C. Clear to this? Now, this question, its answer I would want to know from you. This question, its answer I would want to know from you. Tell me which one is maximum acidic. Tell me which one is maximum acidic. My dear students, do not directly go into these groups. Do not directly go into these groups. First of all, look carefully. Here you have got carboxylic group attached. Okay. Here also you have got carboxylic group attached. Here you have got OH. This is basically phenol, right? Okay. OH group attached. And you know, acidic strength of carboxylic acids, acidic strength of carboxylic acids is greater than that of acidic strength of phenols. You know that? Acidic strength of carboxylic acids is greater than that of acidic strength of phenols. So A and B is going to be definitely more acidic than C and D. A and B is going to be more acidic than C and D. Now, among A and B, which one is more? Withdrawing. Wherever you see withdrawing, that's more acidic. So A is more acidic than B. Now, among C and D, withdrawing. So C is more acidic than that of D. So A, B, C, D is the order. That's it. That's it. Yes, I believe this particular question is clear. If this question is clear, look at these two questions again. Tell me the order of their acidic strengths. Think over these two questions quickly. These are very simple questions. My dear students, if you see only one fluorine is attached here, two fluorine atoms are attached, three withdrawing groups are attached, right? More withdrawing means more acidic. So C is more acidic, then B, then A. Done. What do you think about this particular question? What do you think? Do not directly jump into the groups. If you see OH, COH, carboxylic acid, right? And carboxylic acids are stronger acids than that of phenols. So C is maximum acidic. Now, among A and B, NF3 positive has got more minus I. More minus I means more acidic. So A, then B. So CAB is going to be the order of this particular question. Yeah? I believe I'm clear with this. I believe I'm clear with this. Okay. These two questions. These two questions, guys. Tell me the answers. Tell me the answers. Tell me the answers. Everyone. CHF3, CHCl3. CHF3 and CHCl3. Which one? Which one, guys? Quickly. Normally, your answer would be, I think A is more acidic than B. Right? But guys, see, if you talk about your CHF3, when you take hydrogen out as H positive, what do we get? We get CF3 negative. When you take hydrogen out as H positive. Similarly, when you take hydrogen out as H positive, what do we get? You get CCl3 negative. CCl3 negative, right? CCl3 negative. This CF3 negative and CCl3 negative, what do I call them as? I call them as the conjugate bases of these acids. I call them as the conjugate bases of these acids. Remember one thing, acidic strength is directly proportional to what? Stability of the conjugate bases. Acidic strength is directly proportional to what? The stability of conjugate bases. So first of all, you have to check which conjugate base here is more stable. Which conjugate base here is more stable? My dear students, carbon carrying negative, then you have got fluorine attached. Carbon carrying negative, then you have got chlorine attached. Right? Carbon carrying negative, then you have got 3 chlorine atoms attached. My dear students, do you know in case of chlorine, you have got vacant d orbitals? In case of chlorine, there are vacant d orbitals. But in case of fluorine, there are no vacant d orbitals. If in case of chlorine, there are vacant d orbitals, can I say there's a possibility of back bonding here? There is a possibility of back bonding here. And let me tell you, back bonding, it increases the stability of this conjugate base. And more stable the conjugate base, stronger is going to be the acid. So among these two acids, which one is more acidic? It is CHCl3 that is going to be more acidic than that of your CHF3. Understood? Tell me the answer of this particular question now. First of all, make their conjugate bases. Take this hydrogen out as H positive. Take this hydrogen out as H positive. Negative charge comes here. Negative charge comes here. You've got oxygen here. Oxygen does not have any vacant orbital. But sulfur has got vacant d orbital. If sulfur has got vacant d orbitals, there is a possibility of back bonding again. And due to back bonding, conjugate base is stabilized. More stable the conjugate base, stronger is going to be the acid. So, which acid among these two is going to be stronger acid? It's going to be A greater than B. Am I clear with this? Say it in the charts quickly. Everybody. Everybody, people. Everybody. Right? Am I clear with this? Perfect. So with this, we are done with inductive effect. And these are the types of the questions which can be asked from your inductive effect. Okay, nothing more than this. That's something which I'm telling you right now. Nothing more than this. Nothing more than this. Okay? Tell me once in the chats if all the things are clear. I want to know it from everyone. Then I'll be starting the resonance. Quickly, guys, quickly, everybody. Tell me in the chats whether all the things are clear. I want to know it from everyone. Quickly, 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 quickly. The chats are running very slow. The chats are running very slow. I want the chats to move fast. I want the chats to move fast. Quick. Exactly. Fire in the chats. Guys, you're supposed to be energetic for these 3 hours. You're supposed to be very energetic. So for that purpose, you have to stay very, very, very active in the chats. Otherwise, it's going to be very difficult. Let me tell you that. Perfect. Done. So let's move on to the second topic. What is that? That's your resonance. Again, I'll be teaching you that stuff in resonance which is asked in your examination. Okay? Nothing more, nothing less. Now, my dear students, what is resonance all about? Let's have a look, first of all, on this particular statement. What the statement says, and accordingly, I'll make you understand. See, guys, whenever a true structure of a molecule, whenever a true structure of a molecule cannot be drawn, or if any structure of the molecule will not explain all the properties of the molecule. First of all, if we cannot draw the true structure of the molecule, or if any structure of the molecule will not explain all the properties of the molecule, at that point of the time, we say the molecule exhibits resonance. What is meant by that? What is meant by that? My dear students, for example, if I talk about benzene, the most common example. If I talk about benzene, if I ask you what is the structure of benzene, if I, for example, ask you what is the structure of benzene, I'm pretty much sure some of you will say, this is the structure of benzene. Okay? Some of you will say, this is the structure of benzene. And there will be a lot of people among you who will say, no, this is not. This is the structure of benzene. Some will say, this is the structure of benzene. Some will say, this is the structure of benzene. Right? Now, my dear students, if I call this as carbon number 1, this 2, this 3, this 4, this 5, this 6, for example. Let's say this 1, this is 2, this is 3, this is 4, this is 5, this is 6. If you talk about the structure number 1, in the structure number 1, if you see, between carbon number 1 and carbon number 2, what do we have? We have a double bond. Between carbon number 1 and 2, there is a double bond. Over here in the second structure, between 1 and 2, there is a single bond. There is a single bond. Perfect. As per this structure, there is a double bond between these two carbon atoms. As per this structure, there is a single bond between these two carbon atoms. Perfect. Right? So, my dear students, you must have studied bond length. If I talk about the bond length, if I ask you to compare this bond length and this bond length from these two structures, what will be your answer? You will say, here you have got a double bond, here you have got a single bond. You will say this bond length should be lesser. This bond length should be lesser than that of this one. Okay, if you look at this one, you will say this bond length should be more than that of this one, because here you have got a double bond. Again, I'm telling you the same thing. If you look at structure number 1, you will say this bond length should be lesser than this bond length, right? Because here is a double bond, here is a single bond. If you look at this structure, you will say this bond length should be more, this bond length should be less. But, my dear students, when you talk about benzene, when you see benzene experimentally, and experimentally it's observed that in case of benzene, all the bond lengths between C and C, they are what? They are equal. Experimentally, it's observed that all the bond lengths in case of benzene are, all the bond lengths between carbon-carbon in case of benzene are equal. So I can say neither this structure, I'll say this particular structure is not able to explain all the properties of benzene. I'll say even this particular structure is not able to explain all the properties of benzene. And whenever a true structure of the molecule cannot be drawn, or a structure cannot explain all the properties of the molecule, we say at that point of time, the molecule exhibits resonance, right? See, this structure is not able to explain all the properties of benzene. Even this structure is not able to explain all the properties of benzene, correct? Right? So I would say benzene will be exhibiting what? Benzene will be exhibiting resonance. I would say some of the information about benzene is given by this structure. Some of the information of benzene is given by this structure. If I compile the two informations, how do I compile the two informations? As per structure number 1, there should be double bond here. As per this structure, there should be single bond. So in actual benzene, here you will find neither pure single bond nor pure double bond. It will be having a partial double bond, right? As per this structure, there has to be a single bond here. As per this structure, there has to be a double bond here, right? But in the actual benzene, there will be neither pure single nor pure double. It will be a partial double bond here also. Similarly, it will be a partial double bond everywhere in case of actual benzene, right? I would say this is going to be the true structure of benzene. This is going to be the true structure of the benzene, which I call as the resonance, hybrid. And these structures I will be calling as the canonical forms. These are what we call as the canonical forms. Let's say this is canonical form 1, this is canonical form 2, This is the true structure of the molecule, which is what I call as resonance hybrid over here. Am I clear to everyone? Am I clear to everyone, people? Quick, everybody. Am I clear to everyone? Yeah? I hope I'm super clear with this and you got to know what this resonance exactly is all about. This is canonical form. This is canonical form. This is your actual true molecule, which is what you call as a resonance hybrid. Okay. My dear students, in canonical forms, you can clearly say between these two carbon atoms, there is a double bond. Between these two carbon atoms, there is a single bond. Between these two, there is a double bond. So I would say the bonding in case of canonical forms is localized. The bonding in case of canonical forms is what? Is localized. Similarly here, you can clearly see there is a single bond here. There is a double bond here. There is a single bond here. There is a double bond here. Right? The bonding is localized in canonical forms. Whereas if you talk about the hybrid, the double bond can be at some point of time here, some point of time here, some point of time here, some point of time here. So I would say here the bonding is not localized. Here the bonding is delocalized. Here the bonding is delocalized. Now, if the question is asked, delocalization is present in resonance hybrid, canonical forms, what will be your answer? In your canonical forms, the bonding is localized. In your resonance hybrid, the bonding is delocalized. Delocalization is actually present in the hybrid, not in the canonical form. Okay? Remember this particular point. Delocalization is present in the hybrid, not in the canonical forms. I hope I am clear with this. Okay? I hope I am clear with this. Now, my dear students, how do we exactly draw the resonating structures? Right? First of all, whenever you see any molecule having a pi bond followed by the sigma bond followed by the vacant orbital. Whenever you see a molecule containing pi bond followed by sigma followed by vacant orbital, that molecule will show resonance. That molecule is going to show resonance. For example, look at this particular molecule. Do you see pi here? Yes, pi, sigma. If you talk about this particular carbon is sp2 hybridized. It has got the vacant p orbital. So I would say pi, sigma, vacant orbital. Whenever you see pi, sigma, vacant orbital conjugation, so there will be resonance in the molecule. And how do I draw its resonating structures? Simply you have to do one thing. Shift this pi bond here. When you shift the pi bond here, what do you get? This is going to be your CH2. Since you are shifting pi bond from this particular carbon, you are shifting pi bond. So positive charge will be shifted to, now this carbon will be getting positive. Then comes a single bond. Then comes your CH as such. Now there will be a double bond here. And this is going to be CH2. Right? If this was canonical form 1, this is going to be your canonical form 2. And similarly, you can make the hybrid as well. How do you make the hybrid? Have a look. CH2. Keep single bond first of all everywhere. CH, single bond CH2. Okay. Now, canonical form is telling you that there is a double bond here. This structure is telling you there is a single bond here. So in the hybrid, there will be neither pure single nor pure double. It will be partial double. Right? Similarly, this canonical form is telling you there is a single bond here. This canonical form is telling you there is a double bond here. So in reality, there will be no pure single, no pure double. So it's going to be partial double. Right? Partial double bond character. This canonical form is telling you that this carbon has got positive charge. But this canonical form is telling you, no, this carbon has got positive charge. So I'll be keeping delta positive here also, delta positive here also. So this is my hybrid over here. This is my resonance hybrid. The point is, whenever you see pi sigma vacant orbital conjugation, resonance will happen there. This was the first case. The second case. For example, look at this particular case. Do you see pi sigma and this is carbon, sp2 hybridized, having the vacant orbital, vacant p orbital. So basically pi sigma positive, pi sigma vacant orbital. Again conjugation is present. So again resonance is going to happen here. So shift this pi bond in this direction. When you shift the pi bond in this direction, what do you get? CH2. Now this is going to be a double bond here. And here, my dear students, since you are shifting pi bond from this carbon, so this carbon gets positive here. Rest, everything is same. Now again, if you see pi sigma positive means shift it in this direction. What do you get? You get CH2, double bond, Now this pi bond has been shifted here, right? So this carbon will be getting positive, and this is your pi bond. Again, my dear students, if you see pi sigma positive, this pi bond shifts in this direction. When this pi bond shifts in this particular direction, what do I get? Again, I'll be writing CH2 here. Now, if you look carefully, this is as such. This pi bond is shifted. This carbon is getting positive. Now, my dear students, again, if you see pi sigma positive, so shift this bond here. When you shift this bond here, this again going to be CH2 positive, and this is going to be its last canonical form. Perfect. So these are different canonical forms of this particular molecule which we had. Now, people, if I ask you how the hybrid will look like, if you talk about the hybrid, this is, for example, your CH2. Okay, this is CH2. Now, first of all, every bond is getting partial double bond. What does that mean? See, this structure is telling you there is a single bond here. This structure is telling you no, there is a double bond here. So in reality, there'll be partial double bond. Similarly, there'll be partial double bond everywhere, right? This structure is telling you this carbon is having positive. This structure is telling you this carbon is having positive. This structure is telling you this carbon having positive. This carbon having positive. So I'll keep delta positive here also, delta positive here also, delta positive here also, delta positive here also. So what do I call this as? This is my resonance hybrid here. This is my resonance hybrid here. Am I clear with this? So this was your pi sigma vacant orbital conjugation. So whenever you see pi sigma vacant orbital, there will be resonance, and this is how you are going to draw the resonating structures. Now tell me, my dear students, in this molecule, will there be resonance? What do you see? What do you see? In this molecule, pi sigma positive. Pi sigma positive. See, phosphorus here is forming 4 bonds. Phosphorus here is forming 4 bonds. 4 bonds means it has got 8 electrons in its outermost shell. It has got 8 electrons in its outermost shell. So will there be any vacant orbital? There is no vacant p orbital here, but in phosphorus there is vacant d orbital. In phosphorus there is vacant d orbital. So you have got pi sigma vacant d orbital, it will show resonance. Again, pi sigma sulfur contains vacant d orbital, it will show resonance. Tell me whether this molecule will show resonance or not. Quickly, I'm waiting for your answers. Whether this molecule is going to show resonance or not. Quickly. Everyone. Whether this particular molecule is going to show resonance or not. Yes or no in the chats. Pi sigma positive. This is nitrogen here. Nitrogen does not have any vacant d orbitals, right? The group second element. It does not have any vacant orbitals. But nitrogen, it has formed 4 bonds here. So its octet is complete. There is no vacant p orbital with nitrogen. D already it does not have, right? P, all are, no one is vacant, right? So this particular molecule is not going to show resonance. For resonance, there should be pi sigma vacant orbital conjugation. Okay? Am I clear, guys? Tell me, in this molecule, will there be resonance? Pi sigma in phosphorus vacant d orbital. Pi sigma vacant orbital. There will be resonance. Look at this one. Pi sigma. Now look at this boron. Boron is forming 3 bonds. So 6 electrons in its outermost shell. It will be having a vacant p orbital. Its octet is not complete. Okay? It will show resonance. Look at this one. Will it show resonance or not? Pi sigma boron. 3 bonds. Vacant orbital. So it will show resonance. So your first type of the molecules which show resonance were your pi sigma vacant orbital. Now there can be pi sigma free radical as well in a molecule. Whenever in a molecule you see pi bond followed by the sigma bond followed by the free radical. Whenever in a molecule you see pi bond followed by sigma followed by what? Followed by free radical. Again in the molecule there will be resonance. How do you make the resonating structures here? For example, this is the case. This is pi, this is sigma, this is radical. Pi sigma radical means there will be resonance here. So how you will be making its resonating structures? So simple, just shift this pi bond in this direction. When you shift this pi bond in this direction, you'll be getting, for example, CH2. Now this pi bond is shifted from this carbon, and that carbon from which pi bond is shifted, give that carbon a radical, single bond, CH, double bond. Now this is going to be just CH2 over here. So these are the two resonating structures which we have made. Simple. Now, my dear students, can we make the hybrid? Absolutely, you can make the hybrid. This is going to be CH2, single bond CH, single bond CH2. Now, there is a double bond here. There is a single bond here. So there will be partial double bond. Single bond here, double bond here. So there will be partial double bond. So, my dear students, this particular structure is telling you that this carbon should have a radical. So keep delta radical here. This particular structure is telling you that this carbon is having the radical. So keep delta radical here. So this is your resonance hybrid here. I believe I'm clear with this. I believe I'm clear with this. Right? Let's take one more example. I'm talking about pi sigma free radical conjugation. Do you see pi sigma radical? Yes, there is pi sigma radical. So again, there will be resonance here, right? Again, you will have to make the resonating structures. So first of all, shift this pi bond in this direction. When you shift the pi bond in this direction, you'll be getting a double bond here. Okay. Now this is the carbon from which pi bond is shifted. Give that the radical. Rest, everything keep the same. Again, you have got pi sigma radical. So shift this pi bond in this direction. What do you get? You get CH2, double bond. And now this is going to be a double bond. This is the carbon from where pi bond is shifted. Give that the radical. Now again, you have got pi sigma radical. So shift this pi bond here. When you shift this pi bond here, it's going to be CH2. This is your double bond. Rest, everything you can keep same. And this particular carbon gets the radical here. Again, my dear students, pi sigma radical. Shift this pi bond in this direction. So what do you get? You get CH2. And this carbon is having the radical. So these are all the canonical forms of the molecule which we have. If you formed all the canonical forms, can we make the hybrid here? Absolutely. Again, we can make the hybrid. So hybrid will look like something like this. Hybrid will look like something like this. So everywhere you are going to keep the partial double bond. There is a partial double bond here. This is your delta radical here, delta radical here, delta radical, and delta radical here. This is your resonance hybrid. Am I clear? Am I clear? Am I clear, people? Say it in the chats quick. Say it in the chats quick. Say it in the chats quick. So this was my second conjugation, which was pi sigma radical conjugation. The third one is your pi sigma negative charge conjugation. Whenever in a molecule you see pi bond followed by the sigma bond followed by the negative charge. Pi bond followed by the sigma bond followed by the negative charge. Like you have here, pi, sigma and negative. Again in the molecule there will be resonance. And how exactly you are going to make the resonating structures here? Shift this negative charge here and shift this pi bond here. What do you get? You get CH2 with a negative charge, single bond, CH, double bond, and this is going to be CH2. Simple. Whenever in a molecule you see pi sigma negative charge, so there will be resonance in the molecule, and this is how you make its resonating structures. Now, my dear students, at the same time, if I ask you to make the hybrid, double bond, single bond, so partial double bond here, similarly, partial double bond here, delta negative on this carbon, delta negative on this carbon. So this is your hybrid over here. This is your hybrid over here. I believe this is clear. I believe this again clear, right? Let me take one more example. If we have it here, yes, we have got one more example. Do you see pi sigma negative? Absolutely. Again, we have got pi sigma negative. So there will be resonance, of course. And how do I make its resonating structures? Shift this here, shifts in this direction. So what do I get? I get CH2 negative, single bond, CH, double bond, and this is your NH. And my dear students, if you want to make the hybrid, you can do that too. CH2, keep first of all single bonds everywhere. Keep first of all single bonds everywhere. Now, this structure is telling you there is a double bond here. This structure is telling you, no, there is a single bond here. So in reality, there will be partial double bond here. Similarly, there will be partial double bond here also, right? This carbon will be carrying delta negative, and this nitrogen will be also carrying delta negative. So this is how your resonance hybrid will look like over here. I believe I'm clear to everyone. If yes, let me know once in the chats. Let me know once in the chats, quick. Everybody. Everybody, people. Everybody. Now, my dear students, since I showed you exactly how you can draw the resonating structures, now the point is, how can you identify which resonating structure is more stable and which resonating structure is less stable? For that, I mean, this question is frequently asked in your exam. You just have to remember few rules and you are done. What are the rules exactly? What are the rules exactly? These are the three resonating structures which are given to us. Look at all of them. Tell me, is there any resonating structure among these three wherein atoms do not carry any charge? Just tell me that. Is there any resonating structure among these three wherein atoms do not carry any charge? I believe the first one. And remember, neutral one is always more stable. So one is more stable. One is going to be maximum stable because atoms do not carry any sort of charge here. Now look at second and third. In second and third, atoms are carrying charge. In second and third, atoms are carrying charge. Now people, just remember one thing. Count these covalent bonds. 1, 2, 3, 4, 5 and 6. 6 covalent bonds here. 1, 2, 3, 4, 5, 6. Again 6 covalent bonds here. Bonds are same. The number of bonds are same. So you are not going to decide on the basis of bonds. If bonds were different, if the covalent bonds were different, then more covalent bonds means more stability. Then more covalent bonds means more stability. But bonds here are same. Okay? So you are not going to decide on the basis of bonds. So on what factors you are going to decide upon? Just tell me that quickly. I'm waiting for your answers. Everyone. Everybody quick. Everybody quick. See, if you talk about this oxygen is carrying negative, this oxygen is carrying negative. So can't decide on that. Here, this oxygen is carrying positive. Here, positive is on nitrogen. Positive on oxygen. Positive on nitrogen. Positive charge is more stable on less electronegative element. Positive charge is more stable on less electronegative element. Among oxygen and nitrogen, which one is less? Nitrogen is less electronegative than oxygen. So I would say 3 will be more stable than 2. So this is the stability order. This is the stability order. Perfect. Look at the second one. Look at the second one. Tell me first of all, by just looking at these three resonating structures, tell me which one will be maximum stable. Tell me which one will be maximum stable. You should not be giving it a second thought. Tell me which one will be maximum stable. Quick. Quickly, guys. See, this is for the first structure wherein atoms do not carry any charge, right? So this first one is going to be maximum stable, followed by. Now count the bonds. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. More bonds, more stability. So 3, then 2. Yeah? Done with this? All right. Look at this particular question. Among these two, which one is more stable? It's pretty much simple. Here, atoms are not carrying any charge. Here, atoms are carrying charge. So A is more stable than B. Right? Among these, A is not carrying any charge. So A is maximum stable. Look at the second one. Oxygen carrying positive, oxygen carrying positive. Carbon carrying negative, carbon carrying negative. Okay? So same atoms are carrying same charge. Same atoms are carrying same charge. Now, are these charges like or unlike? They're unlike charges. Lesser the distance between unlike charges, more will be the stability. Lesser the distance between unlike charges, more is going to be the stability. So B is going to be more stable than that of C. I hope it's clear. Okay, what about this particular question? Among these three, which one is more stable? Is there anyone having no charge on atoms? No, all of them have got charge. Now, count the bonds. 1, 2, 3, 4. 4 bonds here. 1, 2, 3, 4. 4 bonds here. 1, 2, 3. 3 bonds here. So I would say third one is least stable. Third one is C is least stable. C is least stable. Now, among 1 and 2, nitrogen carrying positive, nitrogen carrying positive. So leave it as such. Nitrogen carrying negative, carbon carrying negative. You know, negative charge is more stable on more electronegative element. So negative charge will be more stable here. So A, then B, then C. This is the stability order. This is the stability order. Similarly, guys, This can be again easily solved. First of all, which one is going to be maximum stable? Is there anyone having no charge on atoms? I can see no one like that. So what do you do? What do you do? Count the bonds. Count the bonds. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. More bonds means more stability. That means C and D. That means C and D will be more stable than A and B. Now, among C and D, which one is more stable? See, nitrogen carrying positive, nitrogen carrying positive. Carbon carrying negative, carbon carrying negative. Same charge on same atoms. Is the charge like or unlike? Unlike. Lesser the distance between unlike charges, more the stability. So D is more stable than C. D is more stable than C. Now, among A and B, look carefully. This carbon is having positive here. This carbon is having positive, right? Perfect. Right? This carbon carrying negative. This is carbon carrying negative. Look at this one. Just after this, nitrogen is having a lone pair. So lone pair means repulsions. Repulsions means lesser stability. So A is less stable than B. Or I would say B is more stable than that of A. B is more stable than that of A. Am I clear? Am I clear with all of this, guys? Say it in the chats quickly. Am I clear with all of this? Am I clear with all of this? Everyone? Everyone in the chats. Perfect. Perfect, guys. So now let's have a look on one more important topic, that's cross and extended conjugation. This is again one important point. Cross and extended conjugation. My dear students, understand properly what I'll be saying. Understand properly what I'll be saying. Look at this pi electron pair. Look at this pi electron pair. Look at this pi bond. Look at this pi bond. Pi sigma pi. Do you see conjugation here? Yes. There is conjugation. Pi sigma pi. Again, my dear students, pi sigma pi. Do you see conjugation again? Yes. So I would say this particular electron pair is conjugated on this side as well as on this side. Whenever you see such a case wherein a particular electron pair would be simultaneously in conjugation from two or more than two sides, okay, we call this as the case of cross conjugation. We call this as the case of cross conjugation. Okay. Here, do you see anything like that? No. Pi, sigma, pi, sigma, pi. Right? There is nothing like that. In case of cross conjugation, what happens? In case of cross conjugation, let me tell you one thing you have to remember here. Extent of resonance. Extent of resonance in cross conjugation is always less than that of extent of resonance in extended conjugation, or you can say linear conjugation. Extent of resonance in cross is less than that of extent of resonance in extended. And my dear students, you know, resonance is directly proportional to stability, right? Right? So, if I talk about the extent of resonance in cross is always going to be less than that of extent of resonance in extended. Okay. So on this basis, there can be a lot of questions framed. For example, among these two, tell me which one is more stable. Among first and second, tell me which one is more stable. Quick. Everybody. Tell me, guys. It's a simple concept now. It's a simple concept now. Among 1 and 2, which one is more stable? Just see it like this. Look at this electron pair. Pi sigma lone pair, right? Similarly, you have got pi sigma lone pair. So my dear students, if you look carefully, can I say this particular electron pair, it is on conjugation on this particular side as well as on this particular side, right? So isn't this the case of cross conjugation? And extent of resonance in cross is less. So stability of this one is going to be less. Simple. A is going to be more stable than B. Among these two, pi sigma pi. This is the case of cross. If you see here, pi sigma pi, right? This is your linear conjugation, extended conjugation, and extent of resonance in cross is less. So stability of this particular one will be less than that of second one. Simple. Among these two, see, pi sigma negative. I would say this one is in conjugation on this side as well as on this side. But if you look at this one, you have got pi sigma negative. So I would say this is the case of cross conjugation. This is the case of extended conjugation. So which one is more stable? Extent of resonance and cross is always less. If extent of resonance and cross is less, its stability will be also less. I hope these sort of questions you can easily solve from now on. Okay. My dear students, one more thing which you need to know. What is that? You must have heard that negative charge is more stable on more electronegative element. Negative charge is more stable on more electronegative element, right? Perfect. For example, I've got negative charge on oxygen. I've got negative charge on carbon. Where is the negative charge more stable? I must say negative charge is more stable here. Negative charge is more stable on oxygen. And let me tell you, why is that? My dear students, oxygen has got more negative charge carrying capacity than that of carbon, sorry. Oxygen has got more negative charge carrying capacity, negative charge holding capacity than that of carbon. And remember one thing, the negative charge carrying capacity of one oxygen atom, is even greater than that of the negative charge carrying capacity of 10 carbon atoms. See how stable negative charge will be on oxygen. Do you understand this? You have got OH negative and this particular molecule. Which one would be more stable? Here negative charge is on oxygen. Here negative charge is on carbon. No doubt there will be resonance here. This negative will shift here. Then negative comes here. Again negative comes here. This pi bond gets shifted here. Again this comes here. Again this comes here. Negative charge here on oxygen. And in this particular case, negative charge is spread on 1, 2, 3, 4 carbon atoms. Negative charge on oxygen. And here negative charge is spread on 4 carbon atoms. But you know, the negative charge carrying capacity of oxygen is even greater than that of negative charge carrying capacity of 10 carbon atoms. So which one is more stable then? I would say negative charge is more stable here. I hope you got this. Tell me, A, B, C, which one is more stable and which one is less? What is going to be the order? Everyone. What is going to be the order? Everybody. Everybody in the chats. Everybody. Guys, this is the question which I believe you should be in a position to solve now. You should be. Quickly, guys, everyone. Guys, just give me a second. Are you done? Are you done? Okay, look here in this question. My dear students, if you see carefully, this is pi sigma negative. This negative can come here, and this pi bond can shift in this direction. So I would say negative charge is spread on two oxygen atoms. Look at this one. This negative can come here, and this pi bond can get shifted here, like this. This is one more case. This is one more case, right? Oxygen carrying negative. This is one of the cases. This is one more case. This is one more case, right? If you look at all these three cases carefully, here negative charge is spread on two oxygen atoms. Two oxygen atoms. Here negative charge is spread on four carbon atoms, I must say, right? Here negative charge is spread on one oxygen and three carbon, right? And you know negative charge carrying capacity of oxygen, how great that is. So which one is going to be more stable? I would say simply A is more stable, followed by C, followed by B. Okay, point number one. My dear students, tell me among these two, which one is more stable? There is no oxygen anywhere. There is no oxygen anywhere. This can come here, positive charge can come here, right? Perfect. So positive charge is coming on two carbon atoms. It's being shared on two carbon atoms. But here in this case, it will come on four carbon atoms. More spread of charge, more the stability. Or you can say, among these two cases, wherever resonating structures will be more, stability will be more. So B would be more stable than that of A. Simple. If you solve this question, that means your concept is clear. If you solve this question, that means your concept is clear. You are going to let me know the answer. These are 1, 2, 3, 4, 5, 6. 6. These are not just 4. These are 6. Everyone in the chats. All right. Look here, guys. If you look at the first one, pi sigma negative, this negative can come here, this pi bond can shift in this direction. This negative can come here, this pi can shift on this oxygen as negative. This negative can shift here, then this negative can come on nitrogen. This negative can come here, even this negative can come here, right? Okay. Due to resonance, negative is here. Negative can come here. Due to resonance, negative can come here, negative can come here. Similarly, already on oxygen. So due to resonance, it can come here, here, and here. Now, if you look carefully, look at this one. Negative charge is coming on two oxygen atoms. So maximum stable. D maximum stable. So leave D aside. Done. Now, is there one oxygen anywhere? Oxygen is here, right? No doubt oxygen is here. Perfect. But this one has got more resonating structures. Apart from negative charge on oxygen, this one has got more resonating structures. So E is more stable than that of B. So E and B is over. Now, what are all left? A, C, and F. Here, negative charge is coming on nitrogen. Negative charge is coming on more electronegative element, right? And its stability definitely has to be more. So C is going to be more stable. Now, among A and F, F has got more resonating structures. It has got less resonating structures. So F would be more stable than that of A. Clear with this? Right? Is this particular concept very clear to you? Is this particular concept very clear to you? Is this particular concept clear to everyone? Let's take a short break of 15 minutes and after that, we'll start the mesomeric effect. Okay? But I would want every one of you to be back on time. It is 9:36, 9:46, 9:50. I would want every one of you to be back on time. Everyone means everyone. Okay? Let's take a short break of 15 minutes, but please and please be back on time. We have to complete this and it's not going to take more than 1.5 hours. Don't worry about that. It's not going to take more than 1.5 hours. Okay? Perfect. So be back on time. We'll start at 9:50 and 1.5 hours more. With that, your GOC will be done. Perfect. See you in a while. Are you all back? Yes. Is everyone back? Is everyone back? So guys, tell me, whatever things we discussed till now, is every single thing clear? Whatever things we discussed till now, is every single thing clear? Let me know once in the chats quick. Let me know once in the chats quick, everyone. Everyone, quick. All right. Perfect. So let's move on to one more important topic. What is that? That is your mesomeric effect. This again one important topic from which questions are frequently asked. So people, have a look what this mesomeric effect exactly is all about. Understand properly. Understand what I'll be saying. See guys, whenever any group creates a charge separation, whenever any group creates a charge separation between itself and the conjugated system through resonance, then the group is said to be exhibiting mesomeric effect. What exactly it means and how we can understand this. My dear students, look at this particular part which is in the brackets. Do you see pi, sigma, pi? Right? So whatever I have kept in the brackets, it's a perfect conjugated system. It's a perfect conjugated system, right? It's a perfect conjugated system. You have got pi, sigma, pi. It's a perfect conjugated system. Now, towards this conjugated system, for example, I have attached a group. Let's say I have attached a group. Or for example, I have attached an atom. Okay? Let's say that atom is X, which is having a lone pair. Let's say that atom is X, which is having a lone pair. See, this is already the conjugated system. Now I have attached an atom or group having a lone pair here. Do you see this lone pair also in conjugation? Pi, sigma, lone pair. This lone pair is also in conjugation here. If this lone pair is in conjugation, will there be resonance? Yes, there will be resonance. What will happen exactly? What will happen? I'll say this lone pair will shift in this direction and these pi bonds will shift in this direction. Right? So my dear students, what is going to happen? When this lone pair shifts in this direction, I would say this group gets delta positive and there will be negative charge in this particular perfectly conjugated system. So basically, when I attached a group to a perfectly conjugated system, due to resonance, between the group and the conjugated system, is there charge separation getting created? Absolutely, there is charge separation getting created. And whenever any group creates the charge separation between itself and the conjugated system through resonance, at that point of time, we say that the group is showing mesomeric effect. At that point of time, we say the group is showing mesomeric effect. Am I clear with this? Am I clear with this? Similarly, if you look at this particular one, this is again a conjugated system, and towards this conjugated system, if you look carefully, what we have attached a group Y double bond O. This group is also in conjugation with this conjugated system. You can see pi, sigma, pi. So what is going to happen here? Again, resonance will happen. This pi bond will shift in this direction. This pi bond will shift in this direction. This pi bond will shift in this direction. Due to which this oxygen gets delta negative, and this conjugate system gets delta positive. So can I say when I attached a group with the conjugated system, due to resonance, charge separation got created between the group and the conjugate system? And I told you already, whenever any group creates a charge separation between itself and the conjugate system, at that point of time, we say the group is exhibiting mesomeric effect. So this group as well as this group, both are exhibiting what? Both are exhibiting mesomeric effect, right? Now, if you look carefully, is this group increasing the electron density in the conjugate system through resonance? Yes, I would say this group is increasing the electron density in the conjugate system through resonance. And that group which increases the electron density in the conjugated system through resonance, we say that group shows plus M effect. We say that group shows plus M effect. Similarly, my dear students, is this particular group increasing the electron density in the conjugate system or decreasing it? I would say this group is decreasing the electron density in this system through resonance. And that group which does so, we say that particular group shows minus M effect, right? So whenever a group attached to the conjugate system creates a charge difference between itself and the conjugate system through resonance, at that point of time, we say the group is showing mesomeric effect. It can be of plus M or of the type minus M. Plus M means that group which increases the electron density in the system through resonance. Minus M means that particular group which decreases the electron density in the conjugated system through resonance. Okay, I believe this is clear to everyone. Now, my dear students, I hope this particular point is clear. Whenever the group increases the electron density in the conjugate system through resonance, the group exhibits plus M, otherwise it exhibits minus M. Now try to understand what I'll be saying. Let me give you an example. For example, this is your molecule. This is your phenol, right? Let me make it again here. So first of all, if I only talk about this particular part, benzene, is it the conjugate system? Is it the conjugate system, people? Pi, sigma, pi, sigma, pi. It's a perfectly conjugate system, right? It's a perfect conjugate system. Now, towards this conjugate system, I'm attaching a group OH. I'm attaching a group OH, right? This oxygen here has got two lone pairs, okay? Now, do you see conjugation here? Pi, sigma, lone pair. There is conjugation. If there is conjugation, I would say resonance will happen. This lone pair will shift here. This pi bond will shift in this direction. So what's going to happen? I'll be getting something like this. This is OH positive. There's a double bond here now. This pi bond has shifted in this direction. So negative charge. And rest everything same. Now look carefully. Again, you have got pi, sigma, negative. Pi, sigma, negative. Again, there is conjugation. So again, this pi bond will shift in this direction. So what do we get? This is your OH positive. This is your OH positive. Now this, sorry, I have done the wrong thing. Just a second. Here you have got pi, sigma, negative. Now this negative will shift here and this pi bond will shift in this direction. So what do you get? This is your pi bond now. Now this particular carbon carries negative and this particular bond remains as such. Now, my dear students, again, do you see pi, sigma, negative? Yes. So this negative charge can shift here and this pi bond can shift in this direction. So what do you get? You get OH positive. OH positive. And this pi bond remains as such. This pi bond here. And here you have got negative. Again, you see pi, sigma, negative. This negative can come here and this pi bond can shift in this particular direction. So what do we exactly get? What do we exactly get? This is pi bond, this one more pi bond, and now this becomes your OH. Perfect. So people, do you see, if I make the resonance hybrid, how exactly am I going to make the resonance hybrid? Understand. This is your OH. Every bond here is getting a partial double bond character. Even this bond is getting the partial double bond character. I'll keep delta positive here on oxygen. I'll keep delta negative here, as well as here. right? So this is your hybrid over here. So do you see carefully? On the group, there is positive charge. In the conjugate system, there is negative charge coming. So this group is increasing the electron density in the conjugated system through resonance. So that particular group, which increases the electron density in the conjugated system through resonance, we say that group shows plus M effect. So OH shows plus M effect over here, right? One more thing. My dear students, this is your ortho position and this is your para position. Do you see, due to resonance, charges are only getting generated at ortho and para position? Charges are only getting generated at ortho and para position. At meta position, charges are not generated. Talk about any structure. You will not see any charge at meta position. So you can say something like this: mesomeric effect does not operate at what? At meta position. Remember this particular point, this is important. Meso does not operate at which position? At the meta position. I hope I'm clear with all of this. This was your plus M showing group. Now similarly, let's say you have got a molecule like this. Let me draw it again so that it will be very clear to you. Let's say you have got C, double bond O and H. Okay. So first of all, this was your benzene, which was a perfectly conjugated system. And towards this conjugated system, I have attached a group. Now, if you look carefully, there is pi, sigma, pi. Pi, sigma, pi, right? So the group is also in conjugation here. The group is also in conjugation here. If the group is in conjugation, resonance will happen, right? This pi bond will shift in this direction and this bond will break in this direction. So my resonating structure will be something like this. C, oxygen carrying negative. This is your H. Here you have got a double bond. And my dear students, look at all the other things. This is pi, and this is the carbon from which the bond has been shifted. So this carbon will be getting the positive charge here. Okay. Now, if you look carefully again, pi sigma positive, again there is conjugation. So what will happen? Resonance will happen, right? So this pi bond shifts in this particular direction. So what do I get? This is C, oxygen carrying negative. This is hydrogen, double bond, and rest, almost everything same. So this is a pi bond here. There'll be a positive charge here on this particular carbon. This is now the same. Again, if you see pi sigma positive, right? This pi bond breaks down in this direction, right? So what do you get? This is pi, positive, oxygen carrying negative, and this hydrogen. Okay. Again, do you see pi sigma positive? Again, this bond will break in this particular direction, right? Okay, and when this bond breaks in this direction, what do you get? You get C, and you get double bond O. This is H. And this is going to be pi, and pi here. Perfect. Now, my dear students, these are all the canonical forms which are made over here. Now, the point is, can we make the hybrid in this particular case? We can absolutely make the hybrid also. Leave the hybrid aside. Tell me one thing. When I attach this group towards this perfectly conjugated system, is this group creating the charge difference between itself and the conjugated system? Yes, it's doing so. So this group again is showing mesomeric effect. Now which one? Plus M or minus M? Is this group increasing the electron density in the conjugated system? No, it's decreasing it. And that group which decreases the electron density in the conjugated system through resonance, we say that particular group shows minus M effect, right? That particular group shows minus M effect. Am I clear with this? Am I clear with this, people? Quickly in the chats. Okay, I hope this is clear. My dear students, there are few points which I would want to share with you, and do remember them. Okay, do remember them. First of all, this is your plus M series. Like I showed you in the beginning, plus I series, in the similar way, you have to remember your plus M series, right? Plus M power of NH2 negative is maximum, right? Followed by your O negative, NH2, NHR, NR2, etc., etc. This is the series which you will have to remember. This is the plus M series of the groups. Similarly, there is one more series which I would want you guys to remember, that is your minus M series. That is your minus M series. This is your minus M series, which again you have to remember, because without remembering these two series, you won't be able to solve the questions. You won't be able to solve the questions. Okay. Now, people, after remembering these two series, we can directly move on to the application part of this particular mesomeric effect. Let me first of all tell you, mesomeric effect dominates over hyperconjugation, which we have not discussed yet, okay, which dominates over inductive effect. Remember this particular case. Mesomeric effect, it dominates over hyperconjugation, and hyperconjugation dominates over what? Inductive effect. Now, what about the application part? What about the application part? My dear students, first of all, if I talk about the stability of carbocation, carbocations are stabilized by what? Electron donating groups. Carbocations are stabilized by electron donating groups, right? I'll give you the order over here, and remember this order. Remember this order, what I'll be telling you over here. Stability of carbocation is decided by plus M. Plus M showing group, plus M showing group. It increases the stability of the carbocation to the maximum. After plus M, plus H. After plus H, it's plus I. Then it's going to be minus I. Then it's going to be minus H. Then it's going to be minus M. This is going to be the order which you can remember to solve the questions which are based on stability of carbocation. Okay? So, if you have got two molecules, let's say in one molecule, a group is showing plus M. In one more molecule, a group is showing minus I. So, which carbocation will be more stable? The one in which group is showing plus M. I'll show its examples in some time, but before that, I would want you guys to remember these things. If I talk about the stability of Carbanion, Carbanions are stabilized by electron withdrawing groups. Electron withdrawing groups. And you know, mesomeric always dominates over hyperconjugation, hyperconjugation dominates over inductive. So, I'll first of all give priority to minus M, followed by minus H, followed by minus I, followed by plus I, followed by plus H, followed by plus M. In this order, you are going to solve your questions. Okay. Similarly, if I talk about your acidic strength, I told you already, electron withdrawing groups, they increase the acidic strength, right? And here, electron withdrawing, I'll prioritize minus M first, then minus H, then minus I, then plus H, and at the end, plus M. Similarly, basic strength is increased by electron donating groups. And here I'll prioritize plus M first for that, then plus H, then plus I, then minus I, minus H, and minus M. These are the respective orders which, if you remember, you can easily solve the questions. For example, guys, this is my first question. Arrange the following according to their stability order. Arrange the following according to their stability order. First of all these are your carbocations, carbon carrying positive everywhere. Okay. Now look at the groups. Look at the groups which we have. OH. OH is present at para position. OH is present at the para position. Oxygen has got lone pair, right? So it can show resonance. So I would say this group shows plus M. It shows plus M, right? OH at meta position. At meta position, mesomeric effect does not operate. So at meta position, it will operate its inductive effect, normal, minus I. Okay. Nitro, NO2. Nitro shows what? I told you already, it shows minus N. You have seen the series, right? Nitro shows inductive also. Perfect. But you know, mesomeric always dominates over anything. Mesomeric dominates over hyperconjugation as well as inductive. So I'll consider the most dominating factor of nitro here, that is mesomeric, minus N. Okay. Look at this one. Nitro here is at meta position. At meta, mesomeric does not operate. So I'll consider its minus I. SH. Sulfur has got two lone pairs. So it will show plus M here. It will show plus M. Order we have to give the stability order. Carbocation stability, right? Carbocations are stabilized by, I gave you the order already, plus M maximum followed by plus H, right? So which one is plus M showing? This is plus M showing. The last one is also plus M showing. Now, OH or SH, which shows more plus M? OH shows more plus M in the series, right? So 1 is going to be maximum stable, followed by 5. So I have done plus M showing groups. After plus M, is there any one showing plus H? No. After plus H, give priority to plus I. There is no plus I showing. This is minus I. This is minus I, right? This is more minus I. Nitro, more minus I. More minus I means more withdrawing. More withdrawing means it will destabilize this. So among this and this, which one is more stable? I would say 2 is more stable than 4, right? And at the end, I'll prioritize third. This is going to be the stability order. Is this particular point clear to everyone? Is this particular point clear to everyone? Yeah? My dear students, for example, you have got a question like this. This is your question. These are your carbanions. These are the carbanions. You have to arrange them as per their stability order. Can you do it? Carbanions. Now, first of all, carbanions are stabilized by electron withdrawing. So first you will be prioritizing minus M, then minus H, then minus I, then plus I, then plus H, at the end plus M. This is the order which you will be considering. First of all, look at this particular group, NH2. NH2 shows which effect? Plus M. It's a plus M showing group, right? NH2 at the meta position. Nitrogen is more electronegative, so simply minus I. OH at the para position, it will operate plus M, right? PR3 will operate minus M. PR3 positive will operate minus M. Now, which one is operating minus M? The last one. So, stability of the last one is maximum, right? After minus M, minus H. There is no minus H showing. Minus I showing is second. After minus I, plus I. There is no plus I. There is no plus H. There is plus M. This is plus M. Even this is plus M. Now, which one shows more plus M? Which one shows more plus M? NH2 or OH? NH2 or OH? NH2 shows more plus M. More plus M means it is more donating. More donating means it will destabilize the carbanion. So 1 is going to be least stable. 3 is going to be more stable than that of 1. Right? This is the order. Am I clear with this? I believe these sort of questions you should be in a position to solve easily from now on. Okay. Arrange the following according to their KB values. KB means basic strength order. Remember, basic strength and KB, they are directly proportional. More KB means more basic strength, right? Similarly, more Ka means more acidic strength. More Ka means more acidic strength. So we have to give the order of KB. So we have to give the order for basic strength technically, right? Now, first of all, this is OH at para, so plus M. SH at para, so plus M. O negative at para, so plus M. CH3 at meta, right? It shows plus I. It shows plus I. Now give the order. Basic strength. Basic strength order is decided like this. Plus M maximum, followed by plus H, followed by plus I, followed by minus I, followed by your minus H, followed by your minus M. So what is going to be the order of this particular question? Basic strength order. Is there anyone showing plus M? Yes. This is plus M, this is plus M, this is plus M. Now which one shows more plus M? O negative shows more plus M. So 3 is going to be maximum basic. Now among 1 and 2, which one shows more plus M? OH or SH? OH shows more plus M. So 1, then 2. At the end, I'll prioritize 4. So this is going to be the order over here. I hope I am clear with this particular question as well. Okay? I'm sure this is clear. Now, my dear students, let's move on to one more topic, that is aromaticity. This is again a set of, there is again a set of questions which are asked here, right? And in these questions, you are supposed to check which one is aromatic, which one is not aromatic, which one is anti-aromatic. This is easiest among all, provided you just know their concept. And what is their concept? Let's have a look. First of all, if you talk about, see guys, just a second. Let me tell you, my dear students, experimentally, some of the organic chemistry compounds, some of the compounds in organic chemistry, they were found out to be extra stable. Experimentally, some of the compounds in organic chemistry, they were found out to be extra stable. Okay? And there were some features common in those compounds. There were some features common in those compounds. First of all, those compounds which were found out to be extra stable, we call them as the aromatic compounds. And there were some common features in these aromatic compounds. What were those common features? What were those common features? First of all, the molecule was cyclic. The molecule was cyclic, number one. The molecule was planar. The molecule was planar, number two. There was complete cyclic conjugation present. There was complete cyclic conjugation present. And the molecule was following Huckel's rule. The molecule was following Huckel's rule. That means there were 4n plus 2 pi electrons involved in the cyclic conjugation. What it means, you'll get the idea in some time. First of all, take a note of all these things. I'm telling you, experimentally, a set of organic compounds were found, which were found out to be basically extra stable. And those compounds were named as aromatic compounds, and there were some common features in those aromatic compounds. They were cyclic, they were planar, complete cyclic conjugation was present, and they were following the Huckel's rule. There were 4n plus 2 pi electrons involved in the complete cyclic conjugation. If I take the n value as 0, the value comes out to be 2 pi. If I take the value of n as 1, 4, 1, 4, 4 plus 2, 6 pi electrons. If I take n as 2, 4 to 8 to 10, 10 pi electrons. If I take n as 3, 4, 3, 12, 12 plus 2, 14 pi electrons. Now, similarly, my dear students, there were again one more set of molecules found, which were found out to be very unstable, right? Which were found out to be very unstable. And those compounds were named as anti-aromatic compounds. Again, in these anti-aromatic compounds, which were found out to be very unstable, there were some features common in them. Number one, these molecules were also cyclic. They were also planar. There was complete cyclic conjugation present. Okay. There was complete cyclic conjugation present, but there were only 4n pi electrons involved in the complete cyclic conjugation. If I take the n value as 1, the value comes out to be 4 pi. N value 2, 8 pi. N value 3, 12 pi. What exactly it means, I'll tell you it in some time. Similarly, my dear students, those molecules which are neither aromatic nor anti-aromatic, those were called as non-aromatic. Those were called as non-aromatic. First of all, these were found out to be very stable, highly unstable. Their stability was in between them. Their stability was in between them. So first of all, if I talk about the stability order, aromatic compounds are maximum stable, followed by non-aromatic, followed by anti-aromatic. Followed by anti-aromatic. Okay. Now let's try to use all these things in the questions and we are done. And we are done. See guys, these are some molecules which you have to identify, whether they are aromatic, anti-aromatic or non-aromatic. How do you check them? First of all, do you see this particular molecule? It's planar. I mean, it's cyclic. It is cyclic. Every carbon is sp2. sp2 means planar. So this molecule overall is planar. It's cyclic as well, planar as well, right? Now, is there complete cyclic conjugation? See, pi, sigma, pi, sigma, pi, sigma. There is complete cyclic conjugation present. Now, how many pi electrons are involved in the complete cyclic conjugation? 2, 4, 6. 6 pi electrons are involved. And 6 pi comes in which category? Aromatic. So this particular compound is aromatic in nature. Simple. Look at the next one. Look at the next one. Is this cyclic? Absolutely, this particular molecule is cyclic, right? Is it planar? sp2, sp2, sp2. Planar, right? Now, is there complete cyclic conjugation present? Check that. Pi, sigma positive, pi, sigma positive. Complete cyclic conjugation is present. Now, how many pi electrons? Only 2 pi electrons are involved in complete cyclic conjugation. 2 pi means, what is it? Again aromatic. Again aromatic, right? Again aromatic. 2 pi electrons comes in this category. 2 pi, 6 pi, 10 pi, 14 pi, right? Look at the next one. 2, 4, 4 pi electrons. 4 pi electrons means anti-aromatic category, right? Look at this particular carbon. It has got 2 hydrogens attached with it as well. So it's forming 4 bonds. So I would say this sp3 hybridized. sp3 means tetrahedral. So this molecule is non-planar. This molecule is non-planar. It's not planar. The molecule which is neither aromatic nor anti-aromatic, that is going to be non-aromatic, right? See, aromatic as well as anti-aromatic, they're planar. So non-planar one is non-aromatic. Simple. What about this one? This particular carbon, right? It is also forming 4 bonds. So sp3, sp3 means non-planar, non-planar means this is non-aromatic. This is how you check whether a molecule is aromatic, anti-aromatic or non-aromatic, right? If you look at this particular molecule, my dear students, whenever you see such kind of the molecule, you only see circumferential resonance. Circumferential resonance means this is pi, sigma, pi, sigma, pi, sigma everywhere on the circumference. You need not to consider the ones in between. You need not to consider those pi bonds which are in between. Okay. So first of all, check it out. 2, 4, 6, 8, 10, 12, 14. There are 14 pi electrons involved in the circumferential resonance. 14 pi comes in which case? Aromatic. Simple. Okay. So for aromaticity only, the circumferential resonance has to be taken into account. This is again one more important point. Okay. This is benzene, which already we have seen this is aromatic. Now 2, 4, 6, 8, 10, 12, 14. 14 pi electrons means again aromatic. Look at this one. 2, 4, 6, 8, 10. 10 pi electron means again aromatic. Okay, again aromatic. Alright, look at this one. 2, 4, 6. 6 pi electrons means again aromatic. Right? 2, 4, 6, 8, 10. 10 pi electrons means again aromatic. Is this lone pair in conjugation? Yes. Pi sigma lone pair, conjugation. So I have to consider this as well. So 2, 4, 6. 6 pi electrons means aromatic. Among these two lone pairs, there is one lone pair in conjugation. So 2, 4, 6. 6 pi electrons means this is also aromatic. Right? So that lone pair which is in conjugation has to be taken into account. Okay. Among these two lone pairs, this is the lone pair which is in conjugation. So 2, 4, 6. 6 pi electrons means aromatic. Okay. 2, 4, 6, 8, 10. 10 pi electrons means again aromatic. This particular carbon is sp3 hybridized because it has got 2 hydrogens attached with it as well. Right? So it's going to be non-aromatic. Even this is going to be non-aromatic because this particular carbon is sp3 hybridized. Okay. I believe this is also clear. Look at this one. Just 2 pi electrons means aromatic. 2 to 4, this negative charge. 2 to 4, 4 pi electrons means anti-aromatic. Right? 2 plus 1, 3. 2 plus 1, 3. 3 pi electrons. So which category does it belong? 2 pi neither comes in aromatic nor anti-aromatic. So this is going to be non-aromatic. Right? 2 pi electrons, aromatic. This particular carbon, sp3 hybridized. So non-aromatic. Correct? This is how you can solve these questions easily, and I believe you can do it now. 2, 4. 4 pi electrons means anti-aromatic. Right? This is aromatic. This is non-aromatic because this carbon is sp3. This is 2 to 4. 4 pi electrons means anti-aromatic. So by just looking at the molecules, you should be in a position to check whether the molecule is aromatic or anti-aromatic or non-aromatic. Correct? Look at this one. I believe you can easily solve it now. What is this particular molecule? You tell me in the chats. I'm looking at your answers. What is this particular molecule? Aromatic or anti-aromatic or non-aromatic? Quick, everybody. Quickly, guys. I'm waiting for your answers. Perfect. What about this one? What about this one? Quickly. What about this one? Look at this particular carbon. Do not ignore this one. This sp3 hybridized. So this non-aromatic. This one, 2, 4, 6, 8. 8 pi electrons means anti-aromatic. Right? 2, 4, 6. 6 pi electrons means aromatic. Right? Now, I believe these sort of questions you can easily solve. Okay, tell me this one. See, This particular one is aromatic. This one is non-aromatic. Let me tell you, aromatic plus non-aromatic makes it aromatic. Aromatic plus non-aromatic makes it aromatic. Okay. What about this one? This is aromatic. This is aromatic. Aromatic plus aromatic makes it aromatic only. Okay. Perfect. Right, guys? The next one, 2, 4, 6, and 8. 8 means anti-aromatic. Anti-aromatic, right? Look at this particular carbon. It's sp3 hybridized, so non-aromatic. So these sort of questions, I believe, like you should be able to solve now. See, guys, cyclic conjugated, pi, sigma, pi, sigma, pi. Cyclic conjugated unsaturated hydrocarbons are called as annulenes. First of all, the molecule has to be cyclic, right? It has to be conjugated. There should be conjugation throughout present, right? So cyclic conjugated unsaturated hydrocarbon is called as annuline. So this is one annuline. This is one more annuline. Okay. This is what I call as annuline 4. This is what I call as annuline 4. 2 plus 2, 4. This is one what I call as annuline. This is what I call as annuline 8. 2, 4, 6, 8. Annuline 8. Now, in case of annuline 4 and annuline 8, annuline 4, 4 pi electrons means anti-aromatic, 4 pi electrons involved in the cyclic conjugation. But in case of annuline 8, my dear students, in case of annuline 8 normally looks like anti-aromatic because it has got 8 pi electrons involved in the cyclic conjugation. But remember, it has got a tub-like structure. Annuline 8 I'm talking about. It has got a tub-like structure due to which it becomes non-planar. Due to which it becomes non-planar. And if it is non-planar, that means it becomes non-aromatic. Normally we say, if you just look at the molecule, you can say there are 8 pi electrons. So it should be anti-aromatic. But due to its special structure, a tub-like structure, its planarity is lost. So it becomes non-planar. And if it becomes non-planar, it becomes non-aromatic. Remember this particular case. Okay, have an eye on it. Annuline 8. Similarly, if you talk about your annuline 12, right? Annuline 12 is also non-aromatic. Remember it. And this is your annuline 246. Annuline 6 as usual, which is benzene, right? And benzene is nothing but aromatic. Okay. All right. If you look at this particular case, 2, 4, 6, 8, 10. 10 means it has to be aromatic. But, my dear students, this particular carbon, it has got hydrogen attached. Between these two hydrogens, there will be repulsions. Due to repulsions, it becomes non-planar. Non-planar means it becomes non-aromatic. Remember this particular case as well. Okay. Similarly, this one, 2, 4, 6, 8, 10. 10 means aromatic. 10 pi electrons means aromatic. This particular case, do remember directly. Okay. This particular case, do remember directly. Now we have got the last topic left, that is hyperconjugation. But my dear students, my head is aching right now. So hyperconjugation, I would request you to watch from this particular session. This one last topic, I would request you to watch from, go to the playlists, and in the playlists, open this playlist. And when you open this playlist, here you will find the GOC somewhere. Yes, this is the GOC. And the last topic here, okay, is hyperconjugation, which is started from 9 hours 12 minutes. Okay, the last end part, this hyperconjugation, please do it from here because my head started aching. Tell me, are all the things clear, guys? Whatever things I discussed with you, are all the things clear? I'll be doing a session on purification of compounds as well, don't worry. I hope all the things are clear. The next chapter, first of all, is going to be chemical bonding. And after chemical bonding, I'll do isomerism, okay? Next chapter is going to be chemical bonding, then I'll be doing isomerism. Then all the other chapters also I'll be doing, don't worry. Okay, and let me know in the comment section how you liked the session. Did you get benefited out of this session? I would want to know that from you, from your comments, okay?